Okay, okay. Thank you very much for the occasion to speak here and for the introduction. So my purpose is to talk about something which is very, I think, quite well known, but I will start slowly, which is often called a variety of characters. And I like to use a fancy word, which is skins, but you'll see that it's not really that's not so complicated. So let me start. Well, and then I will go I'll try to find some geometric interpretation. So we will start with algebra with the basic construction. So, okay. Uh, can, can you see the screen properly? Because I see many things. Okay, thank you. Because I'm not so used to Zoom, because we use Team in my university. So let me start with the construction of the schema or the variety of representations. We have gamma, which is a finitely presented group, okay, with some generators and some relations. And we consider the set of all representations of gamma into a Lie group, and our Lie group will be SL2C matrices with complex number, 2 times 2 matrices with determinant 1. Well, this embeds in some affine space. So for each representation, you look at the image of each generator. So these are n copies of the Lie group, and this embeds into affine space. And well, this is an algebraic object, yeah, because the relations give me some polynomial equations on the coefficients, and it's called often the variety of representations. Why are we interested in this? Well, people isn't as looking at this for many reasons in geometry and topology in dimension 3. The main one is because this is related to hyperbolic structures, okay? If the group of isometries of orientation preserving isometries of H3 is precisely the quotient of this group by plus or minus the identity. So we could look at representations into PSL2C, but you'll see that it's easier to work explicitly with this object here, with SL2C. And there is all this well-known coloration theory from the 80s, the A polynomial, and many things, many things. And I will talk about it today. Okay, so let's look at the algebraic structure. So the title of the slides is variety of or a scheme of representations. And why? Because I'm interested in the algebraic structure of this. So people call it a variety, but it's not a variety. Why it's not a variety? Because a variety, traditionally you assume that it's irreducible, it has only one component, and it's reduced. Reduced means that it doesn't have multiple points. But for instance, we may have a polynomial equation which is x squared equals 0. It's not the same as x equals 0. You say as a variety it's the same. Yes, it's the same point, but as a scheme, it's not. Yeah, and the goal here was to look at this richer structure. So essentially, when we talk about a scheme, well, a scheme can be complicated, but we'll talk about affine schemes. These are just algebra subsets here, defined by polynomial equations. But these equations, we don't have any control. It's not reduced, it's not irreducible, so we may have multiple points. And somehow with my co-authors, Michael Heusner, we were looking at these multiple points and whether there is a geometric interpretation or not. Okay? So when I write a scheme, don't be well, the word is a big word, but a fine scheme is just polynomial equations, and I don't take I may take multiple points. That's the idea. Okay. So, but we don't talk about varieties, or representation, we talk about characters. Why characters? Because, well, we want to take the quotient by conjugation, yeah? So when we have conjugate representations, we assume that they are the same or they are equivalent. We want to look at this quotient, and it's well known that this quotient is not Hausdorff, or maybe not Hausdorff, because that's not a compact group. So what does people do? People look at characters. And the character of a representation can be seen, it's just a map that goes from the group, from a discrete group gamma to C. And to each element, I map it to the trace of rho of gamma. So that's the character of the representation rho. maybe I should start over, yeah? So given a representation, its character is this map, okay? And this is used to look at the quotient. And there is, for instance, there is the following lemma that is easy to prove. If I take two orbits by conjugation, then they may be disjoint, but the closures intersect if and only if the representations have the same character. So the idea is that the variety of characters will be the characters will be kind of house of quotient. And in fact, it is a house of quotient. It's more than that. There is a theorem of Processi that I will explain later in the next slide that says if I consider the set of all characters, so characters or representations, that's what we call an algebraic quotient. So, and to distinguish it from the topological quotient, is instead of one bar, we put a double bar. So what does this theorem say? It says that there is an algebraic object, an algebraic variety, in fact, an algebraic scheme that is the natural quotient of that. And this is what I want to explain in the next slide. So in fact, I want to explain the algebraic structure of this set of characters, okay? This set of all representations, or characters or representations. So for this purpose, I need to look at the dual guy. The dual guy is the same, is instead of looking at character from gamma to C, I look at a polynomial map from the scheme of the variety of representations to C. So to each representation, I map the character or the trace of the row of gamma. So which is the same as the character of row evaluated at gamma. Well, this is a subset of Cn. What Processi proves is an algebraic subset with these coordinates, with some coordinates for some elements. And that's not an algebraic variety. It's again, it's an affine scheme. So it's defined by polynomial equations that can be reduced, that can be have multiple points, etc., and so on and so on. And this is called the scheme of characters. So let me explain just a little bit, give me a couple of minutes of algebra to explain a little bit how Processi proves that, because it's not, at the end, it's not so complicated. So this is a little bit algebraic, but it's just to understand the structure. So what people do in algebraic geometry, they look at polynomial functions. Polynomial functions are maps, polynomial maps from the variety of representations to C, polynomial, well, just polynomials there. And we look at the ones that are invariant by conjugation. The algebraic theorem says that this is finally generated by the trace functions of finally many elements, gamma 1, gamma n, capital N. So, and that's the definition of algebraic geometry. So it's the algebraic object, the algebraic scheme, or the algebraic variety with the property that the polynomial functions are precisely the polynomial functions on the variety of characters which are invariant under conjugation, okay? And in this way, okay, these are the generators, so we'll take this as the coordinates. And this gives me the embedding into Cn. And that's how it works. And what Processi proves is that, well, there are some relations and so on, okay? And what we say a posteriori is that points here are characters because they are just determined by the traces. Okay, that's more or less the idea. Okay, so let's go to an example. Let's go to an example because this is not as complicated as it seems. And let me start with a classical example, which is due to Fricke and Klein. So it's more than 100 years old, or it's about 100 years old. So let me start with the free group on two generators, E and B. And what Fricke-Klein proof is that the variety of the scheme of character for the free group is isomorphic to C3. So it's the affine variety or the affine scheme. And the coordinates are the trace of A, trace of B, and trace of the product, AB. So algebraically, what's the algebraic translation of that? The algebraic translation is that as the polynomials, the functional algebra or the functional algebra of polynomials is this scheme. It's just the polynomial algebra on three variables, T8, Tb, and Ta times b, and there are no relations. Or if you want to translate it into practical terms of computable terms, every time you give me a word in A and B, so an element on the free group, Each trace function is just a polynomial on these three variables, T8, Tb, and Tab. And it's a unique polynomial. If it was not a unique polynomial, it would be a question of that, but it's not. It's just a unique polynomial. Okay. So let me talk a little bit about the proof because the proof is it's very nice and it's computable. So what it uses that it uses trace identities on the for matrices from SL2C. Okay. So the first trace identity, which is works for every matrix group, is the trace of A times B is the same as the trace of B times A, and gives the following trace identity. Okay. The second one is that the trace of A minus one is the same as the trace of AB. Okay, this is true only for SL2C. That's not true in general, but this almost all also gives me a trace identity. And the third one is a little bit more involved, but it's a consequence of Cayley-Hamilton equation, for instance, is that the trace of A times B plus the trace of A times B minus 1 is the trace of A times the trace of B. Okay? And in words, you write this equation. And this one is important now because this looks at the scheme relation, okay? And this we'll use this fact later. So we have these relations on groups of two elements. And what Fricke-Klein do, they use these relations to reduce every word into a polynomial into these three variables. Yeah, for instance, if you take a squared, so just use this relation with gamma equals mu equals a, and you get immediately, well, the trace of the entity is 2, so you immediately get this guy. Another one is, for instance, you have to work a little bit more. If you take a commutator, a times b times a minus 1, b minus 1, what you get is this polynomial. And so on. You could work forever on that. I mean, that's very explicit, that's computable, and that's not complicated. Okay? What happens if you have a free group with more elements? Well, this is also known, but the description is not so easy, it's more complicated. Yeah, for instance, if you take F3, you get something of dimension 6, which is a hypersurface into C7 and so on. It's just one equation, and in general, it's quite complicated. It's a computable issue I mean, it's complicated to compute. What you can prove is that this, as a scheme, this is irreducible and has no multiple points. It's reduced. This is really a true variety in this case. But for a group in general, it will be not. So the problem is the following one. Our goal is here. So you start with a finite presentation of a group, finite many generators as some relations. So we can see it as a scheme from the free group. Okay. So the question is, how do I compute the actual scheme? How do I use the relations to compute my scheme of characters? Okay. And that's the issue. So for instance, if I have a free group on two generators, it will be a subscheme of C3. How do I compute it? And well, there are some relations, and that's the question. Okay, and this question was solved by Montesinos 30 years ago, Montesinos and González Acuña. In fact, they didn't care about the schemes at all. But I remember that Montesinos said, okay, there is all this theory. What I want to compute a guy explicitly. I have some equations and so on. So what Montesinos, or González Acuña and José Mari Montesinos did is, okay, I don't care about multiple points. I just look at a variety. So multiple points, I forget it. So starting from a presentation, starting from a presentation here, how do I compute this variety as a superarity of this one, which is given by Magnus? So they say, okay, if I have some relations R1, Rm, they impose these two families of equations. The trace of the relations is 2, because we want that this element is identity, and the trace of the relations times a generator equals the test of the generator. Okay, this is somehow these are relations that need to be satisfied. And what they say that this is sufficient to get the variety of representations as a set. eh? They get all characters as points. Algebraically, you take the radical ideal. It's just taking the radical ideal. So to forget about double, triple points and so on, just take what it's called the radical ideal. If you have x squared, you take x, something like this. Okay. So what we did with Michael Heussener from Clermont-Ferrand 30 years later is that okay, let's take care of multiple points and compute it as a scheme. What relations do we need? So we were using the same relations as Fico and Montesinos, well, we need to add one more family of relations. So instead of taking the test of the relation times a generator equals the generator, we had to say take couples of generators. In fact, you can take one less than the other and impose these equations. So with these famous equations, we know how to compute the variety of the scheme of characters, and we get the multiple points and so on. Okay, and this is somehow well, this is the theorem we prove, and I will not prove it because the proof is not. It's elementary. It's a lot of algebra, but just indicate two main steps. The first one is that well. I I have a starting family of equations, so there's every time I have two words gamma mu in the group in the free group that give the same element in gamma, okay, I impose this equation that the trace of gamma equals they have the same trace, and that's relating to the skin algebras. I mean, Krzyzewski and Sikora and Adam Sikora they prove a theorem that says that the skein algebra at evaluated at a equals minus one equals the algebra of functions of the variety of characters. Okay, well, you can take a manifold with this group and so on, a three manifold, and they prove this theorem. And from this, it follows easily that all you need is to impose these relations. Well, this is an infinite family of relations, of course, because uh, you have infinite this kernel. The kernel from the free group to gamma is usually infinite, infinitely generated by, but you need using trace relations. So the relations from the previous slides and some more relations of due to Max and so on, you reduce to this equation. So that the theorem is just an elementary computation. But what I want to talk uh, is the following thing. Okay, you have this, but now why do we care about multiple points? Okay, so this can be seen in the theorem. You can do a lot of theory and all that. Just yeah, a minor remark that this is you can put this in a computer, but computing is hard. Huh? And if you have simple groups and so on, it's easy. But as long as your group is complicated, uh, you need to work hard to compute. But this is maybe another problem. Well, this is in fact another problem. Okay. So in the next slides, I want to put three examples. So what do I care about the multiple points? Okay. So I will compute three. I will explain the computations of three varieties of characters. Or sorry, three schemes of characters. So let me start with the Fourier knot that you're probably familiar. Yeah, in this conference you are familiar with it. So A and B are two generators. These are two meridians. Okay, maybe not those ones. I don't know, but that's a presentation for the exterior of the Fourier knot. Well, as we said for the computation of Fricke and Klein, we had uh, this is a subset of C3 because the trace of A, trace of B, and trace of A times B are generators, but they are conjugate, yeah, because these are two meridians, and you look easily from this that I think that there is I don't know which this one and this one, this conjugates A and B, so they have the same trace. So that's good, yeah, because we just need two variables. So in fact, every time we have a two-bridge knot, a knot generated by two meridians, it's a plane curve in C2. These plane curves can be very complicated, but if you start with a small a small node like the fluid node or this, you get not too complicated plane curves. So you apply the algorithm, and we get this plane curve. That it has two components. Well, it's not a variety, but it doesn't have multiple points yet, but just has two components. So this component here is the component of abelian representations. Okay, why? Because if you write uh, if you write the trace of a squared, the trace of a sorry no yeah the trace for an abelian representation, a and b go to the same element. So somehow you would have the trace. Let me write it like this: of a squared. Okay, this is oops, I wrote it in the previous slide. That's x squared minus 2. Sorry about my handwriting, but these guys are abelian. Okay, and those are geometric. Those corresponds to hyperbolic structures. So there is one point when x equals plus or minus 2. These are lifts of the hyperbolic holonomy, okay? And you get a couple of complex values for y. All these are lifts of the complex holonomy, complex conjugate, and so on. And you have a whole curve because you probably know the proof of Thurston's hyperbolic filling. When you deform these representations, you get many incomplete structures, and the complete structure is the filling. Okay, so that's the object we get. We get two guys. One which is from algebra or just abelian representations, and this one that comes from hyperbolic geometry. And here you can apply Kardashian theory and so on. So on. You have many things going on here. Okay, but if I'm interested in multiple points. Okay, so instead of looking at this complement, I will look at an orbifold. So I have noticed that I put a label 3 here. So this means I will look at the orbifold with underlying space the 3 sphere. The branching locus will be located at the figure 8 node, and the ramification index is 3. So this means that every point in the figure 8 node has non-trivial isotropy group, and the isotropy group is a group of rotations over the 3. Well, if I want to look at the variety of characters or representations or the scheme of representations, what I need to do, I need to add a relation. I need to look at the fundamental group and get this relation, okay? So now that's the group of this, of a three-dimensional orbifold, uh, a closed one. What happens at the level of variety of characters? Well, if I add a relation, I will add more equations, okay? So here's a brief explanation of what happens. I have two sides. One is just, okay, I cut intersect with x equals minus 1, and that's a condition for an element to be of order 3, okay? If you think it's minus 1 is minus 2 times the cosinus of pi over 3 or 2 pi over 3, or it's pi over 3, okay? And this is why I get this. And we also get the trivial representation. So we can apply the algorithm and compute all this and so on. In fact, we are more interested in this one, and this line x equals minus 1 is tangent to that curve, okay? Because if you replace x here by minus 1, is the computation which is made here, and what we get minus y minus 1 squared. And that's a double point. Yeah? And you can say that the line x minus 1 and this curve are tangent. Okay, that's why we get a double point. And the question is why this is a double point? And the explanation I try to give in the next slide is that, well, this orbifold is Euclidean, and the double point is related to a lift to SU of the rotational part of the lunar. Okay, so let me explain this in the next slide. So that's a Euclidean 3 orbifold. That's the first lines are a summary of the previous slides. Sorry. And my variety of my scheme of characters has 3 points, 2 single points, the trivial representation, That one, which is just the meridian to an element of order 3, but the two meridians A and B go to the same rotation of order 3. And here they go to rotations of order 3. They have two, but they are different. They rotate along two axes that intersect. Okay? And that's the double point. And why this is a double point? That's I would like to explain to discuss why. So it has to do with the Euclidean holonomy. In fact, this orbifold is Euclidean. I didn't write it in the slide, sorry, but that's the question of Euclidean three-manifold by a symmetry of order 3, and we get some fixed points. So this is well known that is a Euclidean orbifold. So it has a representation into the isometric group over R3. So we look at what we call the rotational part because we have this exact sequence, okay? So the rotational part and the kernel consist of translations. So the rotational part is just a question of SU2, of PSU2, and this leads to SU2. So what this point is here is just a representation to SU2 that corresponds to the rotational part of the holonomy, well, lift of it. And what happens with the translational part? Well, the translational part is there, but we don't see it as a representation. We see it as an infinitesimal represent deformation. Okay, so in fact, as Lie algebra, this was what Lou was explaining in the previous talk. As Lie algebra, R3 is the same as SO3, which is SU2. Okay, and well, there is a whole theory of infinitesimal deformations, cohomology, and so on, which I will not explain here, but that's well established. When you look at the translational part, in fact, it corresponds to an infinitesimal deformation. And this is why we get a double point. It's not a deformation of the representation. We cannot deform it, but we can deform it up to first order. And oops, sorry. That's what I was interested in. Okay. Let's look at a second example, a little bit more involved. Well, not much more, but which is the Whitehead link. So I consider another orbifold with underlying spaces 3, branching locus the Whitehead link, and I put these ramification indices on one component 4 and the other 8. Okay? And I look at this variety of characters, or scheme of characters. It has many points, 21 simple points, and 2 triple points. I'm interested in these triple points. Well, these triple points, again, they correspond to some geometric structure because instead of 8, 4, let me put labels 4 here and 2 here. This orbifold has an Euler structure. But the problem is that elements of order 2 are always a problem when lifted. So I put 8 and 4 because I need to lift elements of order 4 in base U. They give me elements of order 8 in SU. Okay, so I need to double the coefficients here, and this has to do with the geometry. I don't know if you are familiar with the geometry, but there are also exact sequences like for the isometries of Euclidean space, and one is an exact sequence is like this. You go from the isometries of nil to the isometries of R2. Okay, that's what people call, or Thurston call, a fiber geometry, and the kernel is R. And still, the isometry group of R2 itself, it has an exact sequence. You look at the rotational part, matricial part, which is in O2 now, not SO2, but O2, and the kernel consists of translations of the Euclidean plane. Well, the issue is that, well, this O2, you put it into as a subgroup of orientation preserving isometries of the free space. And in fact, the group of isometries of nil is orientation preserving, and this goes to PSU2. So what are these two triple points? These two triple points are Richter representations into SU2. So we get two of them because, well, that has to do with the orders, even and on and so on. Two representations into SU2. These are the translational part of this guy. But the rotational part, sorry, if I look at this part here, this is an infinitesimal translation, so it's at least a double point, but this is one step further, and that's a triple point, okay? So what is amazing is that these multiple points have to do with geometry somehow in these examples. Okay, and so let me show a last example. A last example. And this last example, it's not an orbifold. Now it's not really a knot. It's not a knot exterior, but it's a manifold which are constructed from two pieces, K and C. And I log this. K is what? This is K stands for Klein bottle. And this is the orientable interval bundle over the Klein bottle. So it's a manifold with one boundary component, which is the two torus. And this two torus, in fact, it's the orientation covering of the core of this manifold, the Klein bottle. Okay. The other one is a cable space, which is, well, it's a stereo of a torus link, but uh, here is a picture. So it's this, you take a solid torus and you remove this curve, the blue guy here. So what you get, one neighborhood of the blue guy, you get a manifold with two boundary components. And this manifold is a Cypher fiber, yeah, because there is a singular vibration of the torus with a singularity of order 2. And what you do is you remove just a curve, was a regular fiber. And that's a cable. And in fact, if what we do is we recall one of the boundary components of the cable with this manifold, this orientable interval bundle over the Klein bottle. Okay, that's the manifold we construct. So the question is, which one of the components? It doesn't matter. It's reversible. You can exchange. You can say that you can take a bundle over the sphere with a singularity, Cypher fiber bundle over the sphere with a with a just one singular fiber, and you remove two generic fibers. It's the same. Okay, so the blue and the black can be switched. You get the same manifold. So I don't care which one I glue. Well, but I have to specify. Yeah, I have to specify the gluing map. That's true. Okay. So what's the fundamental group of the cable space? So you have two generators, A and C. A is a peripheral element, the blue or the black. It's not important which one. And C is the curve, is the element around the singular curve. So C squared is a generic curve. Okay, that's a presentation of this guy. So they commute. This is what I brought here. So what are the peripheral subgroups? One is the A and the fiber, and the other one is A times C. So if this is A, for instance, A times C is the other one. So the C is a loop around this singular fiber, and also times the fiber. And the fundamental group of the manifold is the Klein bottle, and the peripheral subgroup is the index 2 subgroup, this fundamental group of the two torus. Okay. Which homomorphism we consider? We consider, well, just this one. We map gamma to A. So gamma is this element here, and gamma times mu squared to the generic fiber. Why this one? Yeah, because we found this example somewhere else, because this example was also considered to find essential surfaces not detected and so on. Okay, so I will say something about this. So we didn't invent this example. We just copied from somebody else. So let me just describe the scheme of characters. The scheme of characters is, well, the fundamental group is an amalgamated product. And, to compute it, it's easier to work with just two generators. And you can prove, working a little bit, that this group has this presentation, has two generators and this relation. You work out, we apply our algorithm and so on. It has two generators, so it embeds in C3, yeah, because you just need three elements, trace of two generators and the product. And apply the algorithm, you get a lot of components and so on, but one of the components is that one. And is that one, if you realize X is just a polynomial on Y and Z. So it's just a line. It's homomorphic to a line, but we have Y squared. So uh, it's a double line, okay? And just this is just an example. So where do we got this example? There was a, it was, I think I should have prepared that. Sorry. It was Zhang and somebody else. They had an example of surface which is not detected by the variety of characters. And the surface is the amalgamated torus here. And there are weird things that happens here. And from the point of view of the skins, we get a double line. So somehow what we get is something like weird because that's a, I don't know, a manifold. A manifold, this three manifold has some topology, maybe too easy, maybe too complicated, I don't know. So more than giving a big theorem here, what we have a research program is try to understand this double point is this this phenomena from the point of view of geometry. So we have, for the moment, we are having fun with examples, and we'll see if we get something general. Okay. So I will just finish with a picture of the of the cable and the basis. Thank you for your attention. I cannot hear you.